All right, so let's begin with the units and dimensions, the first chapter. So now we know, of course, we know what is a quantity. What's a quantity? Anything which can be measured is a quantity. Okay, so we are going to talk about the measurements, right? Units, dimensions, measurements. So quantity is anything that can be measured. For example, 10 apples, okay, 5 kg sugar, etc. The number of students in this class, okay, 1 2 3 4, anything, right? Or number of girls in your class, number of boys in your class, that is a quantity. Okay, so then next is physical quantity. What is a physical quantity? The quantity which is related with the properties of matter, okay, property of material or a system, that can be measured. So that property should be able to or that thing should be able to we should be able to measure that. Okay, for example, length, mass, time, force, etc. These are physical quantities. Okay, so then anything we measure has a unit. Okay, so what's a unit? Unit is a reference standard for measurement. So this is standard definition. Unit is arbitrarily chosen and internationally accepted reference standard for measurement. So for example, suppose you want to measure my length. My length means my height you want to measure. Okay, and you don't have anything else. Suppose you are handed up with this pen. I give you this pen, and then you measure my length. Suppose 1 2 3 4 5 6 11 pens. Suppose that's my height. So what will be the unit? Unit will be the length of this pen. Okay, so height of snail sir is 11 pens. But then this is not an accepted unit, right? Because I have this pen, I can hand it over to you. Okay, though this is virtual conference, but everybody will not have this pen, the same pen, right? So it is very difficult for the acceptance of this unit. So the unit should be such which is available everywhere, right? It should be available, easily available. Okay, and it should be accepted everywhere. Okay, so these are requirements of standard. It should be invariable with place and time. Okay, it should not change from this place to that place, and it should be easily available and easily reproducible also. Okay, because if you make, for example, you make 1 kg weight, okay, you should be able to make thousands of those, because you want to distribute them, okay, for measurement in each and every part of the world. So that's why it should be easily available and reproducible also, right? So now different parts of world had different systems of units, and the most widely used were FPS, CGS and MKS. So now what is system of unit? So earlier there were only 3 quantities studied in physics. 3 quantities means only one subject called as mechanics, then the thermodynamics, the electricity, magnetism, etc. It was added later. Then there is modern physics, it was added later. If you talk about 16th century, there was only one subject, that is motion, mechanics. Okay, so any quantity in mechanics you can represent using length, mass and time. So if you have unit of those 3 things, you have system of units, and that's why these were the system of units. FPS was used in some part, okay, then CGS was used in some part, and MKS was used in some part. Okay, so what is FPS? So in FPS system, the unit of length is foot, unit of mass is pound, unit of time is second. Okay, that's FPS. In CGS, unit of length is centimeter, unit of mass is gram, and unit of time is second again. And in MKS system, the unit of length is meter, unit of mass is kg, and unit of time is second. Okay, so these were used in different parts of the world, right? Because for example, suppose there is a country, okay, or there is a kingdom, right? Then they will make their units depending on their convenience, right? Based on their convenience. Okay, so there is a story, how did this FPS system, not FPS system, this foot came into practice. There was one king and he just announced that the unit of length in our country, in my kingdom, from tomorrow it will be my foot. That's it. Okay, and then it became the unit of length. I don't know how true it is because foot is a little bit big, right? Okay, anyways, so these are systems of units. Out of this, the important one is MKS, because now this one is internationally accepted. Okay, so see, if there are different systems of units and you know only about them, you don't know about the conversion factor, then what will happen? Suppose in your country CGS system is used and you talk with somebody where the MKS system is used. Okay, you don't know about MKS, that person doesn't know about the CGS. Then what will happen? If you are talking about anything, any scientific discovery suppose, or let alone scientific discovery, you are talking about your NEET problem, right? NEET physics problem. Okay, then you won't understand what that person is talking and he won't understand what you are saying, right? That's why there should be one internationally accepted system. Okay, and that is known as SI system. Okay, so what is a SI system? So in SI system there are some fundamental quantities and their units are fixed, and based upon those units of all other quantities are derived. Okay, and this thing is known, this thing is internationally accepted. Okay, this thing is internationally accepted. So what are fundamental quantities? The quantities which are defined through measurement. Okay, these are quantities which are defined through measurement, right? And they don't depend upon any other physical quantity for their measurements. So their units are predefined. Their units are defined I'm sorry, based upon their units, the units of other quantities are defined. This thing is clear, everyone? Okay, so they are known as fundamental quantities. For an example, length is a fundamental quantity. To measure length of something, you don't need to know about what's the time, right? What time it is right now. So length doesn't depend on whether it's morning, whether it's evening. Okay, so this is the fundamental quantity, right? This is very basic, but this is fundamental quantity, right? What is derived quantity? For an example, if you want to measure velocity, okay, how will you measure velocity of something? So some body is traveling and you want to measure its velocity, then you need to measure the length, distance covered by that body, right? And also the time, because the velocity will be what? Displacement, to be particular, displacement divided by time. So you need to know about length, you need to know about the time. So you need to know two quantities at least. So these quantities, derived quantities, they depend upon two or more, okay, two or more fundamental quantities for their measurement, right? Actually it's one or more, because there are few derived quantities. For an example, area. If you want to measure area, then what do you need? You need length and breadth. So you can say some power of length. Area will depend on some power of length, right? So you can say one or more. They depend on one or more physical quantities for their fundamental quantities for their measurement. This is clear? All right, good. Okay, so now let's look at the SI system. So what are the fundamental quantities in SI system? So mass, length, time, electric current, temperature, the amount of substance and luminous intensity, these are the fundamental quantities. Okay, so the symbols for them is mass is denoted by small m, length is denoted by small l, okay, time is denoted by small t, that's small t, right? Then current is denoted by capital I, temperature is denoted by capital T. Then amount of substance, you know that from chemistry, right? It is denoted by small n. that is number of moles. Okay, that is quantity of a substance, amount of substance, it's denoted by number of moles. And then there is luminous intensity, it is denoted by IV. Okay, or I nu. Okay, so then what are their units? So units are, unit of mass is kg, kilogram, the unit of length is meter in SI units. Okay, unit of time is second, then unit of current is ampere, unit of temperature is Kelvin. Okay, then the unit of amount of substance is mole, and unit of luminous intensity is candela. Okay, and their short forms are these: kg for kilogram, m for meter, s for second, a for ampere, then k for Kelvin, mol for mole, okay, and cd for candela, right? Then you can notice that here some units are written in small case letters, okay, lowercase, and some are written in capital letters. So what could be the difference? Can you tell me? Okay, so the difference is this ampere is name of a scientist. Okay, Kelvin is also name of a scientist. So if unit is given after somebody's name, then its symbol is written in capital form. Okay, because we write names starting with capital letters, right? That's why. And the full name of a unit, it's always written in lowercase letters only. Okay, this is clear. This is just a rule. Okay, so there might be a question, pinpoint question like this, I don't know, there was never. Okay, all right, so these are 7 fundamental quantities. Then now these 7 fundamental quantities only are not enough, we need 2 more quantities, but they cannot be called as fundamental quantities because they depend on the fundamental quantities, but to measure lot of other quantities we require them, that's why they are known as supplementary quantities. And what are they? One is plane angle, the other one is solid angle. Okay, so what is plane angle? Plane angle is the angle that we know about from our childhood, right? It's 2 lines like this. Okay, 2 lines kept, 2 lines intersecting at a point, or 2 lines starting at a point. Okay, this structure is known as plane angle, right? So that's plane angle. So how do we measure that? So there is a SI system of units. In SI system of units, what we do is, suppose this is a circle and this much arc of a circle makes an angle theta at the center, right? That means if you join end points of this arc at the center, you get this angle theta. Okay, so this angle is measured as length of this arc divided by the radius. Angle is measured as arc length divided by the radius, right? And this is in terms of, or in multiples of radius, that's why the unit is radians. Okay, the unit is called as radians. In short form, it's written as RAD, or its symbol is RAD. This thing is clear, everyone? Okay, good. Then what is the maximum angle an arc of a circle can make at the center? That's 2 pi, right? We had seen this earlier in the first lecture. Okay, why is it so? Because maximum arc length is equal to 2 pi r. If you divide that by r, radius, then that r gets cancelled out, and therefore maximum angle subtended by any arc of a circle is equal to 2 pi. That's simple, right? 2 pi radians, and that is 360 in degrees. All right, next one is the solid angle. So the plane angle is the one which you can draw on a plane, right? Plane means a flat surface you can draw that angle on a flat surface. Okay, so this is angle in 2D, 2 dimensions. Why 2D? Because to draw any flat surface, to think about any flat surface, you need x-axis and y-axis, right? You need two axes, so that is 2 dimensions. Okay, so then if you think about 3D, 3 dimensions, then you will get a solid object. You get solid objects in 3D. So next is solid angle. What is solid angle? It's angle in 3 dimensions. Okay, and now to think about solid angle, how will you get solid angle? So you take, for an example, you take this angle like this, and you just rotate, you keep this point, okay, the vertex of angle as it is, and you rotate it like this. So what will you get if you rotate an angle by 360 degrees? Think about the shape that you are getting. You get a cone like this, right? So that cone is called as 3D angle. Good, very good. You get a cone. Okay, so that cone is called as 3D angle. Now the question is how to measure that. So to measure the plane angle, we took help of a circle. Here we take help of a sphere. Okay, now this thing will look like a circle only because this is 2D paper, or not a paper, 2D tab, right? But this is a sphere. Okay, this is 3D. This is a sphere. Okay, so then here you take some area, small area, large area, any area on the sphere, and you join each and every boundary point of that area at the center. So what do you get? You will get a cone, right? If you take some area, join each and every boundary point of that area to the center, you get a cone, and that thing is known as the solid angle. Okay, and how do we measure that? So it is the perpendicular area by r square. So now here you don't need to think about whether this area is perpendicular or not, because it will be perpendicular. Okay, so radius is always perpendicular to what? The circumference. So in the same way, this radius of a sphere will be always perpendicular to the surface area. Okay, small surface area of a sphere, radius will be always perpendicular, right? So perpendicular area is this one, dA is perpendicular area, and its distance from the center is what? R. Then the solid angle is denoted by this letter, d omega. Okay, small solid angle, sorry. So d omega is equal to what? dA divided by r square. This thing is clear? Okay?
Yes, sir.
Good. Then this letter is known as omega. Then the unit of solid angle measured this way is T radians. Okay, the unit is T radians, and in short form it's written, okay, ST/rad, and most of the times in our textbook etc it's written this way, SR for T radian, right? Then the maximum solid angle, just like we saw the maximum plane angle, the maximum solid angle made by any surface, not just a sphere, a surface which encloses a point, so that surface will subtend maximum of solid angle equal to 4 pi. How is it so? So you have a sphere, suppose, then you just take for omega max, the maximum solid angle, whole surface area of a sphere, that is 4 pi r square. You divide that by r square gets cancelled out, and the maximum solid angle that you get is 4 pi. Right? Okay, good. Next, let's see dimensions. Okay. So now we saw that there are 7 fundamental quantities and 2 supplementary quantities in SI system. So there should be a way to connect these quantities with the derived quantities. Okay, so that way is dimensions. So what is the dimension? It's the power to which the fundamental quantity has to be raised in order to get a derived quantity. The power to which fundamental quantity or quantities have to be raised to get the formula for derived quantity is known as dimension. So it is the relation between fundamental quantities and derived quantities. Okay, so let's come to this first quantity, that is area. So area can be written as what? Now area can be written as length times breadth. Okay, if you talk about a rectangle, then what will be its dimension? So dimension of an area is just equal to dimension of length, right, times breadth is also length. Okay, so we write this quantity like this, okay, in capital letter. So it is L times L, means it is just L square. Okay, it is just L square. So we put that in a box, right? Then similarly, what would be dimensions of volume? So if you think about any formula of volume, the length will come thrice, and that's why its dimensions are L raised to 3, right? Then next is velocity. What is velocity? Displacement divided by time. So that means velocity is length by time. Okay, displacement is length. Okay, d by t. Okay, so what would be dimensions of velocity? Its length in the numerator, time in the denominator. We write that by capital letters. Take the time in numerator. So here it is t raised to 1. In numerator it becomes t raised to minus 1, and that's why the dimensions are L1 t raised to minus 1, right? Next is acceleration. Similarly, you can say acceleration is change in velocity divided by time. So in numerator you have velocity or change in velocity. The unit will be equal to meter per second. That means it is length by time. Okay, so dimensions of numerator are L1 t minus 1, and in denominator you have one more time, okay, t. You take that to numerator, it becomes t raised to minus 1. So you already had L1 t minus 1, and this t minus 1 adds to it, so it becomes what? Dimensions of acceleration are L1 t minus 2, right? That's simple. Okay, next is force. So we know the formula of force is mass times acceleration. So what are dimensions of force? Dimensions of force, dimensions of mass, okay, m, m1. Then dimensions of acceleration we just found, L1 t raised to minus 2. So these are dimensions of force. And then you have energy or work, right? Work and energy are same thing. So the dimensions of that are dimensions of force times displacement, because work done is force into displacement. So you have dimensions of force already, m1 L1 t minus 2. Okay, and dimensions of displacement, this is not second, this is distance, displacement, that is L raised to 1. So therefore you have m raised to 1, L raised to 2, t raised to minus 2, m1 L2 t minus 2. So this is the way in which we can find out dimensions, right? So now why did I find out dimensions of these quantities? Because dimensions of these quantities, they have to be remembered. You need to by heart them. Okay, 12 o'clock in the night, or suppose you are asleep. Okay, you are in sleep. Okay, deep sleep, and somebody asks you what are dimensions of force. You should tell m1 L1 t minus 2, right? Okay, that much by hearted it should be, right? Then you should know the formula connecting these quantities and every other physical quantity that comes in physics. Okay, so that you would be able to find out the dimension of that quantity. Okay, all right. So for an example, find the dimensions of universal gravitational constant. So where does it come? So we have Newton's law of gravity. So force between two masses. So suppose this is one particle or one body has mass m1, there is another body which has mass m2, and they are separated by some distance. They are separated by distance r. Then Newton told us that the force between them is given by the universal gravitational constant multiplied by m1 m2 divided by r square. And therefore now we have the formula connecting force and universal gravitational constant. So we can find out dimensions of universal gravitational constant very easily. Dimensions of G would be equal to what? Just equal to, okay, for that we can write G is equal to F times R square, right? This R square will go on this side in numerator, m1 m2 will go in denominator because we want G only. So G is equal to Fr square divided by m1 m2. So the dimensions are dimensions of force times dimensions of distance square, that is L2, divided by, this is mass times mass, means m to the power 2. Okay, right. So then you have dimensions of G equal to, for force it is m1 L1 T minus 2 multiplied by, you have L raised to 2, and in denominator you have m raised to 2. So this m raised to 1 and the square gets cancelled out, so 1 will remain there. You move that m raised to 1 in numerator, so it becomes m raised to minus 1. So the dimensions finally are m raised to minus 1, L raised to 1 plus 2, that is L raised to 3, and T raised to minus 2. These are dimensions of universal gravitational constant. This thing is clear, everyone? Okay, good, very good. All right, so now that we know how to find out dimensions, let's see applications of dimensions. What are applications of dimensions? So first application is to check if the given relation is correct. So not only given relation, suppose someday you are so much interested in physics that this should not happen, I'm just saying it. You leave your medical field, start studying physics, okay, and not just that, you come up with some discovery like Newton, okay. So you will have some formula, no? Now you want to check whether that formula is correct or not. So first thing that you will do before presenting it to other people is you will check it dimensionally, whether it makes sense or not, whether it is correct dimensionally or not, okay. So that will not happen right, but anyways, so let's see how. So suppose you have this equation, S is equal to ut plus half at square. This is a kinematic equation of motion, and I'm sure most of you know this. S is equal to ut plus half at square, right? So now in this equation there are three terms. One is on left hand side, two are there on right hand side. So the dimensions of all the terms, okay, dimensions of all the terms in an equation should be equal, they should be same, then only it will be correct. It could be correct, right? I will explain why I'm saying it could be correct and I'm not saying it will be correct, okay. So see but if dimensions are not matching, it will be definitely wrong, right? You can check it very easily. S is the displacement, that means dimensions are L raised to 1. Then you have ut, okay, u is initial velocity, t is time. So what will be the dimensions of this? Dimensions of u is the velocity, are L1 t minus 1, and dimensions of time is t1. So t minus 1 plus 1 gets cancelled out, that is t raised to 0. T raised to 0 means it's 1, okay, or a constant which doesn't have a dimension, right? So you have L raised to 1. Constant means what? Numerical constant, okay. Only numerical constants don't have dimensions, otherwise we had one constant here, right? There are too many constants. Universal gravitational constant is a constant, but it has dimensions. Numerical constant means a number, just a number, Okay, numbers don't have dimensions, right? Keep that in mind. Okay, so we check that dimensions of this one and this one are same. Then 80 square, so half will not have any dimensions. Okay, so 80 square, uh, a is acceleration, then you have t square. What are dimensions of acceleration? We just found it is L1 t minus 2. So L1 t minus 2 multiplied by t2. So t minus 2 plus 2 again gets cancelled out. So dimensions are L1. So dimensions of this term s ut and half 80 square, they are same. So given equation is dimensionally consistent, I can say. It is dimensionally correct also. Okay, dimensionally correct. We can make that claim. Okay, so this given equation might be correct. So actually you know that this equation is correct because we have been studying this since 9th standard, I guess. So this equation is correct, right? Because we know it from the study of motion. But then if I write similar equation like this, see this one, s is equal to 3 ut plus 580 square. Is this one correct? Tell me.
Correct only, sir.
It is dimensionally, yeah, good. It's not correct. It is dimensionally correct. Okay, but is it applicable in reality? Is it the correct equation to apply in motion? This equation comes in the study of uniformly accelerated motion. Okay, this is called as kinematic equation. No, I cannot call this one as kinematic equation. Okay, so this is incorrect, right? But this is dimensionally correct because dimensions of this term, this term, this term, they match. Okay, so what number is there in the multiplication with any term, that number we can never find out using the dimensions because numbers don't have any dimensions, right? That's why we can say that suppose you come up with some discovery and you have some formula, and then it makes sense dimensionally, so you can say that it might be correct. Okay, then you have to do various checks to find out whether it's correct or not, right? All right, so let's move on to the next one, and this one now, s is equal to u square t plus at. So of course this will not be correct, right? And we can check it using dimensions. So I can skip this part, right? Shall I skip this? We just want to check whether it's correct or not. And yeah, we can skip this one. Okay, you can check it. I have written it over here. You can check it. It doesn't, dimensions of this term, this term, this term don't match because here it should be what? Ut plus half at square. Okay, so here I have written extra power of u and extra power of t is dropped. Okay, so instead of 2 I have 1 only. So this is incorrect. So dimensions won't match, right? So that was the first application. Next application is to deduce the relation between different physical quantities. Okay, so for an example, the time period of a pendulum depends on its length and acceleration due to gravity. Find the relation between them, right? So you know the pendulum which oscillates like this. Okay, there is a, of course you have seen a pendulum, right? There is a pendulum clock. Okay, so that pendulum oscillates with certain time period. It takes same time for to complete one oscillation. So that time is called as time period, and they say that this time period depends on what? Depends on the length of pendulum and the acceleration due to gravity. So acceleration due to gravity is denoted by small g. So it is just like any other acceleration. Okay, so how to find the relation between them? So what we do is we write t depends upon. So to say it depends upon, we say it's proportional to. It's proportional to what? It's proportional to length, it's proportional to acceleration due to gravity, but we don't know what power of length and acceleration due to gravity will come in the actual formula, right? To what power it's proportional, we don't know. So we put this a and b. Okay, a and b are unknown. So we say t depends upon length to the power a and g to the power b. Okay, so therefore t will be equal to what? T is equal to some constant. Whenever we drop this proportionality sign and put an equality sign, a constant will enter. Constant means what? It will be a number will enter, right? So that's k. K is a number which doesn't have any dimensions. So t is equal to k l raised to a g raised to b. Then what we do is we take dimensions on left hand side and dimensions on right hand side. So you have t raised to 1, okay, and k doesn't have dimensions. Again you can drop k. Then you have l raised to a, okay, then g, because this is just length, so it is l raised to a only. Then you have g raised to b. So what is g? G is an acceleration. What are dimensions of g? L1 t minus 2, because g is acceleration. Okay, L1 t minus 2 raised to b, right? Then what you do is you multiply this l raised to 1 with this b. So you will have l raised to b t raised to minus 2b here. Okay, then you take together powers of l. Okay, that means so you collect the powers of l. So you have l raised to a, l raised to 1b means l raised to b. So that is l raised to a plus b. Then you have t raised to what? You have t raised to minus 2b. And on left hand side you are only having t raised to 1. Right? So on left hand side you only have t, and on right hand side you are having l raised to a plus b. Yeah, exactly, very good. So l raised to a plus b and t raised to minus 2b. So the dimensions on left hand side and on right hand side must match, means there is no l on left hand side. That means what you can say is l raised to 0 is there. Okay, because anything raised to 0 is 1, right? So a plus b must be equal to 0. Okay, and there is t raised to 1 on left hand side, and on right hand side you have t raised to minus 2b. So minus 2b must be equal to 1. So a plus b is 0 and minus 2b is 1. You get these two equations, right? So a plus b is 0 and minus 2b is equal to 1. If we solve them, so take that minus 2 on that side, so we get b equals to minus half. Then we substitute that into the first equation, we get a minus half is equal to 0. Okay, that means a becomes half, a becomes equal to half, right? So we got a and b. We can substitute that in this formula. Okay, in this formula actually, right? So t is some constant k multiplied by l raised to a g raised to b. So what a and b we got? We got l raised to, I mean a is what? Half, and b is what? Minus half. So that is, we have t equals to k l raised to half g raised to minus half, right? Or you can write it as, take that g raised to minus half in denominator, so it can be written as g raised to half. So that is t is equal to k multiplied by l by g raised to half. Okay, and raised to half means what? It's a square root. So t is equal to k square root of l by g. So this is the formula that we can find using the dimensions, and the actual formula is t equals to 2 pi square root of l by g. What does it mean? That constant k is equal to what? 2 pi. Okay, the number is 2 pi, and that we can never find out using dimensions. So this thing is clear, how to find out a particular formula. Okay, good. So now this procedure is simple. Okay, this procedure is simple, but it is time consuming. So if there is a question in NEET, right? So for an example, deduce a relation. Suppose time period depends on this one, you know, right? But there would be some questions like something length depends on the universal gravitational constant, okay, the Planck's constant, speed of light, etc., something like that. Okay, and find out the correct relation between them. So there will be 4 options. You have to choose one option. So that question will take time. So what you should do is you should stop for a while. Okay, you should solve other questions first, and then if you have time, then you should attempt that one, because that will take time. In that time you can solve at least 2-3 questions. Okay, if there is a lengthy question like that, right? Okay, we can take multiple examples of this. This one, force in circular motion depends on the mass of an object, velocity, and the radius of the circle. Find the formula relating them. Okay, so let me just explain this, right? Let us just find it out. Okay, so that you will get a clear idea. So then, see, what is given, that if there is an object moving in a circle, okay, so force acting on that object which is moving in a circle, it depends on the mass of the object, its velocity, and the radius of the circle. It's given. So we don't know what powers of mass, velocity, and radius will come in the formula of force. So that's why we write that force depends upon, so it's proportional to mass to the power A, velocity to the power B, and radius to the power C, right? So then you remove the proportionality sign, you put an equality sign. Okay, so up to this there is nothing difficult, and it is not at all difficult. Okay, even after this. So then you write dimensions on both sides. So on left hand side you have force, on right hand side you don't need to write k. You have mass to the power a, so dimensions of mass is m only, or m raised to 1 to the power a. Then you have velocity. Velocity is L to the power L 1, L1 t minus 1, right? L to the power 1, t to the power minus 1 raised to b you have. And then you have length, radius, so it's L raised to 1 to the power c you have. Okay. Then you can write this thing as dimensions of f. Okay, let me write dimensions of f. So it is m1 l1 t minus 2, and on right hand side what do you have? You have m to the power a only, there is no m in these two terms. Okay, L to the power you have b plus c, right? L to the power b plus c, and t to the power minus b. Okay, that's it. Then we should match dimensions on LHS and RHS. So let's do that. So we got this thing. So if you match dimensions of m, so you get a equals to 1. You match dimensions of L, so b plus c must be equal to 1, right? B plus c is equal to 1, and then you have t raised to minus 2 is minus b, so minus b is equal to minus 2, that means b is equal to 2. You put that here, so if you put that here, what do you get? 2 plus c is equal to 1, so c must be equal to what? Minus 1. Okay, take the 2 on this side, so it's 1 minus 2, so it's minus 1, right? Then you put all this a, b, c in this formula. Okay, so you get f equals to some constant k, m to the power a, which is 1, then v to the power b, b is 2, and c to the power minus 1, sorry, not c to the power, r to the power minus 1, so that is r to the power c, no? So that's minus 1, so it's r raised to minus 1. And then what do you get? So that r raised to minus 1, you can move it in denominator, so you get f is equal to k times mv square by r, right? And the correct formula is f is equal to just mv square by r, and it is called as centripetal force. Okay, centripetal force acting on an object moving in a circle. It is given by mv square by r. Okay, so as we saw, we can't find this k, the constant, the number, we cannot find out using the dimensions. right? This use is clear, everyone? Okay, so now you can see this was a simpler problem. Okay, force depends on mass, velocity and radius. This is simple one. Still it takes some time. I guess it took, I mean, I was explaining this also, but still it will take around 1 minute for the simple problem. But if you have other quantities whose dimensions you don't know, right? You don't by heart. Okay, for an example, the universal gravitational constant, it's very difficult to by heart dimensions of every quantity in physics. Okay, so that's why those kind of problems will be, you should on the first phase you should avoid them. At the end, if you have time, you should solve them. Okay, that's very simple. Your 4 marks will be definite, but if you chase those 4 marks, maybe you will run out of time and you will lose 8 marks. That should not happen. That's why, right? Okay, then let's come to the next use, to find the conversion factor between units of quantities from different system of units. So personally I don't find this one more useful. Okay, but anyways, let me explain this. So suppose you have SI system and the unit of force in SI system in Newton. The unit in CGS system is dyne. Okay, so 1 Newton is how many dynes that you want to find out. So 1 Newton is suppose n dynes. Okay, and you want to find out this n. So what you do is, in first system you write length mass time as L suffix 1 m suffix 1 t suffix 1, and in second system you write it as L suffix 2 m suffix 2 t suffix 2. Okay, these are units of length mass time in the two systems of units. Then once you write that, force in first system, you have dimensional formula for force, which is L1 m1 t raised to minus 2. So the Newton can be written as, because the dimensional formula for force is L1 m1 t raised to minus 2. Okay, so its unit must have these dimensions, right? So in the first system it is L1 to the power 1 m1 to the power 1 t1 to the power minus 2. In second system it is L to the power 1 m to the power 1 t to the power minus 2, right? So this is Newton, this is dyne. So write 1 Newton, which is this thing, L1 to the power 1 m1 to the power 1 t1 to the power minus 2 is equal to n times dyne. Okay, which is L2 to the power 1 m2 to the power 1 and t2 to the power minus 2. Then what we can do is, to find out n, you can just move this thing on other side. Okay, so you get L1 by L2 to the power 1, m1 by m2 to the power 1 and t1 by t2 to the power minus 2 if you move this thing on this side. Okay, and then you substitute what is L1. So m is unit of length in the first system, that is SI system, is meter, and unit in CGS is centimeter. Unit of length in CGS is centimeter, right? Then unit of mass is what? It's kg. Okay, unit in the other system, CGS is what? It is centimeter, gram and second, so it's gram. Okay, then you have second which gets cancelled out. Unit of time is equal. Then 1 kg is how many grams? It's 1000 grams. 1 meter is how many centimeters? Is 100 centimeters. So you put that. So then that centimeter will get cancelled out, right? Here the gram will get cancelled out, and you will get 100 raised to 1, 1000 raised to 1, and then if you multiply it out, it is 10 raised to 2 multiplied by 1000 is 10 raised to 3. So it is 10 raised to 2 plus 3 means 10 raised to 5, right? So 1 Newton is 10 raised to 5 dyne. This thing is clear, everyone? Right, good. So then Now we can do it very easily. We don't need to do all this business. 1 Newton is n dyne. So instead of writing it that way, instead of doing all this business, we can just say 1 Newton is what? It is length raised to 1, mass raised to 1, and time raised to minus 2, no? So it's kg meter per second square. 1 Newton is kg meter per second square. And in CGS, it will be just gram centimeter second raised to minus 2. Okay? This thing is clear? Yes, no? Right? So the second square or second raised to minus 2, second raised to minus 2 gets cancelled out. Then here itself you write this is 1000 gram. Okay? 1 kg is 1000 gram, 1 meter is 100 centimeter, and you cancelled out this thing. Gram gets cancelled out, centimeter gets cancelled out, and here itself you get n equals to 10 raised to 5, and you got it, right? So no need to use dimensions. Actually, in doing this also we use dimensions because we wrote the unit in proper form, right? But there is no need to do all this business. That's what I am saying. This thing is clear? Okay, very good. So then let's see some problems based upon this. Okay, so let's see this one. The physical quantity that has same dimensional formula as pressure is. So can somebody tell me what is pressure? It is perpendicular force per unit area.
Upon area.
Very good. So it is force upon area. Yeah, good, Vishalini. Force upon area. So coefficient of viscosity. Do you know about this? Yeah, pressure is force upon area. Good. Coefficient of viscosity. This question is from 2022, a recent question. Okay, so you might not know. Let me tell you, there is Stokes' law of viscosity. The viscous force, it is the friction in the fluids. Fluid means liquid. Okay, it's given by 6 pi eta RV. Okay, so this is force acting on, suppose a ball is moving in a fluid, a liquid, force acting on that, F is equal to 6 pi eta RV. This is Stokes' law. So there you have eta. Eta is called as the coefficient of viscosity. Okay, so this is coefficient of viscosity. R is the radius and V is the velocity, right? So its dimensions are, okay, so we can find out its dimensions, okay, using this formula. Good. Then you have force. So then you have momentum, and then you have Young's modulus of elasticity. So Young's modulus is the ratio of stress to strain. Now this is little bit difficult. I mean, what is difficult? To explain this thing, because we are just starting this chapter and the formulae from all over the physics will come in this chapter only, okay, because we are studying dimensions, right? So we need to know the dimensions of each and every quantity, sorry, the formulae of each and every quantity, right? So Young's modulus is given by stress by strain. And what is stress? Stress is force by area. Okay, suppose you have a wire like this, some wire like this, and you apply some mass. Okay, so you hang some mass. What will happen? Its length will increase. So suppose L was the original length, L is the original length, okay, and the increment is delta L. So strain is, yeah, strain has no unit. So strain is delta L by L. Okay, delta L by L. It has no unit because this unit of length and length will get cancelled out. So unit of this thing is just same as that of unit of force by area. Okay. So unit wise, you can say dimensions of Young's modulus are same as that of dimensions of force by area. So that is dimensions of this thing are same as that of dimensions of pressure, because pressure is force by area. Okay, so if you just look at all of the options, okay, if you just glance over, not stare, okay, glance over all of the options first before solving for dimensions of this one, dimensions of this one, then you will come to know that dimensions of this one are same as that of dimensions of pressure. Okay, and if you have sufficient practice, then you will immediately click this one, right? So this one very, very simple. This thing is clear, everyone? Okay, good. Let's see another question. Dimensions of this thing, m l t raised to -2 a raised to -2 belongs to the self inductance, magnetic permeability, electric permittivity, magnetic flux. So now this thing we need to check. Okay, so does anybody know? It's option B. Okay, let's check. Okay, so you know all of the dimensions? I don't remember. Okay, anyways, no problem. If you can remember, that's very, very good. If you can remember dimensions of all quantities, very good for you. Then these kind of questions won't take any time for you, right? So let's take self inductance, first one. So we have Faraday's law. EMF induced is equal to L di by dt. Okay, this is the Faraday's law. So current is fundamental quantity, time is fundamental quantity, right? EMF is not a fundamental quantity. So what can you write for EMF? EMF is work done per unit charge. Okay, because I want to relate them. So it is L into di by dt. So I can just say this L is not length, this is self inductance. Okay, its dimensions I want to find out. Times here I have I and T. I can just move these things on other side and I can find out dimensions of L. Okay, so it will be work done, dimensions of work done times dimensions of time divided by I have Q, which is charge, multiplied by current. Okay, so L will be equal to, what are dimensions of work done? That I remember, it is L2 m1 t raised to -2. Okay, then you have t raised to 1. Okay, you found m1 L2 t minus 2 a minus 2. Good. Yeah, so t1, so in denominator q, charge can be written as what? Current is charged by time, so this thing can be written as current into time, and then you have current. Okay, so dimensions of this thing is a. Okay, so what do we get? This time and this time gets cancelled out, L2 m1. Okay, and we got rid of this time and time, t minus 2, and this is current, dimensions are a. So you take that to the numerator, a raised to -2. So that's what you got, right? But this L on left hand side and L on right hand side is different. This is self inductance. Okay, who told me answer? Indusha, was it the same thing?
No, sir.
Oh, so you don't remember correctly. Anyways, no problem. Next one is magnetic permeability. Okay, so you should know a formula for magnetic permeability. Okay, so for an example, where will this formula come? Magnetic permeability, there are lots of formulae. F is equal to ILB. Okay, I will use this one, or I can, yeah, force is equal to ILB, and B I can say is, this is force acting on a conductor which is placed in magnetic field B. Okay, I is the current, right? So then B is I can say mu naught Ni, number of turns per unit length, and you have I. So from this one I can find out the formula for mu naught. Okay, so let's see whether it does whether this one matches. Okay, so here you have length and you have length, so this thing gets cancelled out, I guess. Okay, and then what's there? I means a square is there. Number of turns doesn't have any unit, so you have mu naught divided by this is I square, and on other side it will become a raised to minus 2, right? Okay, so force is equal to L1 m1 t minus 2. Okay, and this thing is I, and I means dimensions are a, that is a square on this side, on other side it will be a raised to minus 2, so that is a raised to minus 2, and that are dimensions of mu naught. Okay, so are they matching? m1 L1 t minus 2 a minus 2, right? They are matching. Okay, so this is how we can find out if we don't remember and if we remember, then this question won't take any time, right? This thing is clear? Yes, no? Okay, all right. If we don't remember, these kind of questions are time consuming. If we remember the dimensions, okay, these are dimensions of magnetic permeability, then it's just not even 10 seconds. Okay, let's see next one. Plane angle and solid angle have. So this is a good question. Dimensions but no units and no dimensions, both units and dimensions, units but no dimensions. What's the answer? It's option D. Okay, we have seen they have units. Okay, we have assigned units to them even though they don't have any dimensions. So they have units but they don't have dimensions. Good. Then the next one, yeah, units but no dimensions. Very good. Unit is radian. Okay, unit for the plane angle is radian, for solid angle it is st-radian. Okay, next one, match list 1 with list 2. Okay, tell me, choose the correct answer from the options given below. So there are dimensions, okay, quantities are given on left hand side, dimensions given on right hand side. So here also we need to know the formulae, right? The gravitational constant we just found. What were the dimensions? I guess this thing, m minus 1 L3 t minus 2. These are the dimensions of G, right? Yeah. So then next is gravitational intensity. Okay, so gravitational intensity is just, gravitational intensity means your small g only. Okay, so what are the dimensions? Small g means what? Acceleration only. Acceleration due to gravity is gravitational intensity. What are the dimensions? Tell me. We'll talk about that, right, when the gravitation comes. Is it D option? Okay, you told the option directly. Okay, I wanted dimensions of this thing. It is this thing, right? It is acceleration, and that's why dimensions are this thing. Okay, then you have gravitational potential energy. So any form of energy will have same dimensions. So that is m1 L2 t minus 2. m1 L2 t minus 2, it's option 4. So dimensions are this thing, potential energy. Let's write this thing as U. Okay, or actually we should have written O. All right, so this 2 is what? It's option A. Okay, this thing is option D, and this one is what? Potential energy, no? So it is B, and the remaining one, so this thing we don't need to check. Okay, L2 T2 is option C. So which one is correct? So A is 2, B is 4. Is it correct? A is 2, B is 4. That's correct. C is 1. C is 1. Yeah. So option A is correct. Yeah, very good. So option A is correct. So this is clear,
Yes, sir.
right? So this is also from 2022. Okay, and this is a good question. Let's see another one. Yeah, let's see another one. Displacement of an oscillating particle is given by y is equal to a sine of bx plus ct plus d. The dimensional formula for ABCD is, tell me. The dimensional formula for ABCD is. Okay, so see, you have y equal to a sine of this thing. Okay, so y is the displacement, means now sine of an angle, yeah, sine of an angle will have no dimensions. Okay, it will be just a number, so numbers don't have dimensions. Then you have a, so this thing doesn't have dimensions, that means dimensions of a are same as that of dimensions of y, right? Dimensions of a and y would be equal. So what is y? It's displacement. So a has dimensions of displacement. Then the sine of an angle, so angle doesn't have any dimensions, right? We just saw angle doesn't have any dimensions. So therefore all these terms, three terms, bx, ct and d, they don't have any dimensions. So you can say that dimensions of bx, it doesn't have any dimension, means you can write this thing as anything raised to 0, right? And anything raised to 0 means what? 1. Okay, so you move that x on other side. So dimensions of b would be equal to what? 1 by x. So 1 by x means x is length. Okay, x is length, so this is 1 by l, that means dimensions of b are l raised to minus 1. Similarly ct, dimensions of ct are also equal to 1. Okay, because this is an angle, angle doesn't have a dimension, means you can just say it's equal to some number. Okay, means 1. Then you can move the c on other side, sorry, t on other side, so it will be 1 by t. Okay, 1 by t means dimensions of c will be equal to 1 by t, that's t raised to minus 1. And what about d? D is dimensionless. Okay, d is dimensionless, means it's just a number, right? Because it's an angle. Okay, so what do we get then? If we multiply a b c d, so a b c d, if you multiply their dimensions, so a has dimensions of length, b has dimensions of 1 by length, okay, or l raised to minus 1, t c has dimensions of t raised to minus 1, and d is dimensionless, that means you can say it's 1. Okay, so l minus 1 and l plus 1 gets cancelled out, it is t raised to minus 1, that's it. T raised to minus 1 is the answer. So it is option B, right? T raised to minus 1 means everything else is 0. This thing is clear, everyone?
Sir, how did you take that A equal to L?
How did I take a equal to L? See, y is equal to a multiplied by this thing, sine of this bracket. Okay, that means what is there inside the bracket? It's sine of something, means the term inside the bracket is an angle. Okay, so sine of an angle is pure number, it doesn't have any dimensions. So y is equal to a multiplied by this dimensionless quantity, right? So you forget about this thing. So y will be what? Dimensions of y will be equal to dimensions of a, right? And what is y? It is displacement, means dimensions of y is same as that of dimensions of displacement, it's length. Okay, and therefore dimensions of a is also same.
Thank you, sir.
Welcome. This one is clear? Yes, no?
Yes, sir.
Okay, good. So now it's 8:35. Let us stop here. Remaining problems based upon this we'll solve tomorrow. Okay. All right, good. So let's stop here. Have a good day. Bye.